All right, so we are in section 1.6. This section will be really quick because most of these problems we'll be discussing in this section will be dealing with the graph, and we can answer most of the question without doing the math. Okay, so all about the, so we have all so this section is all about the transformation of functions. So most of the questions will be like, or problems will be like, we are given a function, we will be given a graph, and we'll show you that how some little change in the equation of a function change the graph. How can you basically transform one graph to another graph just changing the equation, or change the equation, how that affect the graph. So first of all, we'll just look at a couple of common graphs, common functions. I hope that you already know most of those. Some of those might be a little bit newer to you. Okay, now the left one is a constant function, right? We know that. That's a constant function. So what is true about that function? What are the properties? The first property is what is the domain here? You see the x and y's. It can be negative infinity to positive infinity, any points. But the y is a constant value, right? Doesn't matter what point you pick, all the y's are same because that's a constant function for y. And at the same time, this is an even function. What is the definition of even function? We tried to understand the even function, and there are a couple of different ways you can understand. Now, first one was, even function was something which was symmetric about y-axis, right? So both sides of y will be similar. So it has that same property. And also, the even function has another property that if you have a point xy on the graph, you will always have a point minus xy on the graph. Let's say you have a point minus 5, 6. I'm sorry, the 5, 6 is a point on the graph. So there must be a point minus 5, 6 on that graph. So that is true for the first function. Look at the second function. This function is an odd function, okay? But at the same time, we call it identity function, because anytime if you have a function like fx equals to x, this kind of functions is a special version of odd function called identity function. Whenever the function is f of x equals to x. Domain and range, negative infinity to positive infinity, increasing function for sure, right? It's increasing because from left to right is increasing. Every single point, I'm saying every single pair, if you compare between left and right point, it will be increasing. And again, just as, again, there's an odd function. The next one, this is a little bit modification on the absolute, the identity function. The only difference here is f of x equals to absolute value of x. Have you ever heard the absolute value? Okay, now all it matters is in case of the absolute value, it will be always like positive value. Okay, let's say absolute value of negative 5 is 5. Absolute value of negative 10 is only 10. So absolute value just ignores the sign. Okay. And since this is, if you look at here, it was, remember in case of the identity function, it was like this, right? But there is no negative value in this case. So that's why your curve look like a V. Again, domain and range, domain is negative to positive. There is a little change in the range. Range starts from 0. And because you see the range cannot be negative, because none of the value of y can be negative because of the absolute value. Okay, so that's why the range starts from 0 and go all the way to the and you see this graph is decreasing in the left side, right? Because this side is decreasing up to here and then increasing again from here. So we just wrote that it's decreasing from negative infinity to 0 and it's increasing from 0 to infinity. It's an even function because it's symmetric about the y-axis, right? If you look at the both sides of y-axis, you'll see that looks similar. Next function, standard quadratic function. Okay, any quadratic function means that your in your equation there will be a there will be something like x squared, okay, something raised to the power 2. But in general, the standard quadratic function means f of x equals to x squared, okay, and any quadratic function will be similar to this. There might be a little bit difference in their shapes, but the pattern will be something like this. Because the reason we are just telling you this, so that just looking at the graph, you will know, or you can guess, what kind of function is that graph. Okay, so we know that we see the domain and range, and similarly, the left side is decreasing, the right side is increasing, and this function is an even function because it's symmetric about the y-axis, right? Look at the y-axis, and y-axis basically divide the graph into two similar shape. Next one, left side, square root function. Anytime you draw a graph for a square root function, it will be very similar to this. It may be a square root of something else. Let's say, for an example, what do you mean by something else? Something else means instead of root x, it may be root 5x. It may be root 7x. It will look similar to this. It might be, for an example, if I show how it will be different in different situations. For an example, this is the ideal one, right? So for an example, it is some other square root. It will be still similar to this. It may be like this, maybe like this. You see what I'm saying? But it will be, you'll know the pattern that this is a square root function. And the next one, oh, interesting fact. Not even, neither even nor odd, right? Because it has only one half. We don't have the other half, so we don't know exactly whether that is even or odd. So it's basically not even, not odd. The next one, it must be an odd function. It's a standard cubic function where you have a x cubed term, right? Domain and range infinity, increasing for sure between every single pair. And it's an odd function because remember the odd function is symmetric about the origin. So if you have a point xy, you will always have a point negative x, negative y for every odd function. These are some introduction of different graphs. So cubic root function. So the difference between the cubic root and a square root, you did not have anything like this. But this is an odd function since matches all the properties and is symmetric is symmetric about the origin and increasing domain and range negative infinity to positive infinity. The next one, reciprocal function. What is reciprocal function? F of x equals to 1 over x, or let's say f of x can be 1 over 9x. Okay. Those are the thing. Those are reciprocal functions. Reciprocal functions are interesting. You see the graph is disconnected, right? Because you see you are basically drawing two different graphs. And the domain and range is also interesting because you see the domain is a little bit scattered because for this one we have some domains and for this one we have different domains. So what we did is we just tried to say that okay, this is also one domain and this is one domain, and we used a union. Have you ever seen this operator? This is an operator called a union and it basically joins two different sets. Okay, so this is one set and this is other set. So we are combining both sets. Same we did here, and again it's decreasing in different here. Okay, so it's decreasing in most of the points. Is decreasing here as well, but the rate is not that high. But for an example, between here to here, the rate is extremely high. And it's an odd function, as you see. If you have a x, y point, you must have negative x, negative y form. Okay. Now, these are some basic functions which we just want to know, so that just looking at the function, we know that whether it matches some patterns and we know what the functions are. Remember, in real life, there are plenty of other graphs which will not be matching with these patterns. Though don't assume that doesn't matter what graph you see, it will always fall into these categories. These are the extremely common ones. That's why we want to show you those. Now we will learn that if you just make a little twist in the function of a graph, you can basically shift the graph vertically. Okay? And what is that? For an example, you have a graph, let's say f of x. You know, all of the, at this point, we just know that all the function, all the graphs are some kind of function, right? And that is a function of x. Now for an example, let's say if you just add a constant with the graph. For an example, you add c. C is a constant. Let's say it's a constant 2 or constant 3, a constant 4. You just add with that. What happens? You know, let's say this is the original graph, the black line. Okay, in the left graph. And when you add c with that, your graph will be moved upward, c unit upward. You know, let's say c is 3. You will move the graph 3 unit upwards, but you see still the pattern is exactly same. Still the graph looks exactly same, but the graph is moving upward direction that many units. If the c is 5, the graph will be moving. So that's called a vertical shift, because you are shifting the graph upward. Look at the second example. We have the same thing, but this time we are subtracting c. If you subtract some constant, the graph will move downward, but at the same unit. For an example, if the c is 3, you will be shifting 3 units downward. But look at the graph carefully. The graph still have the same pattern. Okay. For an example, this is another example of vertical shift. Let's say your black line is the original graph, which is x square. What kind of graph is that? Remember the common graph? Standard quadratic function, right? Now, let's say this is the black one, is the original graph. Okay. Now, when you add 2, look at this. When you are adding 2, the graph is moving, shifting 2 units upward. You see how it is moving 2 units? Look at the blue line. It's 2 units, right? 1, 2. And then when you are subtracting 3 units, the graph is moving 3 units downward. As I said before, you know, at this point, we're just looking at these graphs and we are just trying to see whether we can understand that how graph can be vertically moved or shifted just based on some small tweak and twist. Okay. All right, so here we have another example. So what kind of graph was that? Look at the blue line. What is that graph? Absolute function, right? Absolute function. Now let's say you have a graph of absolute function, and if you want to vertically shift that, here the red one. So for an example, if this is x, absolute x, and you just subtracted 4 here, your graph should vertically shifted downward, right? Because you subtracted 4. Look at the equation. Absolute x minus 4, and you just shifted the graph 4 unit down. Again, the same example, but now for this example, let's say we have a absolute function. Can we obtain this one? So we know that this must be something like here, right? Minus 2, and then again increasing, right? Let's look at some horizontal shifts. So for horizontal shifts, so we looked at some vertical shifts. So in case of horizontal shifts, what do we see is, look at the change. We are basically adding the constant with x, not with the function. Do you see the difference? In the last example, in the last category, in case of the vertical shift, we add the constant with the function, right? Now we are adding the constant with the x. So how it is different? So you are basically, for an example, if you have an equation, let's say, if you have a function f of x, now you're replacing that function by f of x plus c whole square. right? Because you are just replacing x by x plus c. Now, if you do the addition, what happens? Your graph moves left side to the left. So you see here we are adding c unit for an example. So your graph original line was the black one, and it basically moved horizontally it moved to the left by that unit. If c is 5, you will moving your graph 5 unit left to your left. And same is true for the subtraction. If you do the subtraction, graph will be moving to right. So here is another example how the graph is moving horizontally. Okay. So here the black line is the original line, and when you added 2, you got the red line. You see the 2 units here? Look at this, 1, 2. It moved 2 units left. And when you subtracted 3, it should move towards right. So it basically moved 3 units to your right from the origin. That is the blue line. Now, can we do this? What is the x square? How does it look like? Okay. So you are moving to the left 1 unit, right? So your graph should intersect this point, right? It will be like u here touching this 1. We'll show you some animation after. I'm saying the combining multiple things. Now for an example, we're combining the horizontal and vertical shifts. So if you look at carefully, let's say the original equation is x squared. Okay. Now can we obtain this, which is x plus 1 whole square minus 3. Now what we did here, we are doing all of those. We are doing vertical shift, we are doing horizontal shift, both of those, right? Because we are doing the vertical shift here because we subtracted 3, right? And we are doing the horizontal shift because we added 1. So it can be all of those. Now what we are doing, for example, let's say this is the original graph, and then first we are doing the horizontal shift. Horizontally we added 1, so we should move left, right? So that's what we did here. We moved left by 1 unit because we added 1 with x, and then we subtracted 3. That means vertically your graph will be shifted 3 units down, right? Look at here. So we were here and we moved the graph 3 units down. So this is going to be a new graph, the green one. So what we are looking at is we have an equation. We know that pattern, but also, for an example, in real life, you may not have this given. Okay, you may have only this one, but you can match. Looking at this, you can guess. Okay, I know what is x square, so it should be coming from x square, right? Since instead of x square there is x plus 1 square, it should be moving somewhere here, and then moving 3 units down because there is a vertical shift. Now I know that we always can draw the graph just from a couple of points, but sometime when, let's say, you were discussing with someone, you don't probably want the perfect graph. I'm saying you probably don't want all the points and draw the graph perfectly, right? Sometimes you want to just show the pattern and you want to discuss on that. Okay, so just if you just know some basic things like this, just looking at the equation, you'll be able to draw the graph. That will not be the perfect one, but that will work. You can at least make some sense. Or sometime, let's say you are reading some literature and it might referring some graph which is not drawn there, but the equation is given. But just by looking at the equation, you can visualize yourself that how the graph will look like, if you just know some of these basic things. Now, again, we are doing both of the shifts here, right? Vertical and horizontal shift. So x plus 1, you'll be moving from here to here, and then 2 units upward, right? You are doing vertical shift, but that is positive, so your graph will be moving to this point. Right? This is the point your graph will be moving. Any question? X plus 1, this one? Oh, here, as you remember that, let's go back. Remember, in case of the vertical horizontal shift, when you have some addition, you move left. Yeah. And when you have subtraction, you move right. Yeah. Any other question?
Yeah. How do you know whether it's horizontal or vertical?
Oh, because when you have something added to the x, you know that is the horizontal part. When that is added to the equation, something like this, for an example, the plus 2, that is added as a constant to the equation. So that is the vertical shift. Because remember, look at this. Let's go back to the horizontal and vertical shift, the basic definitions once again. Look at this here. The c is added just as a constant to the whole function. Look at the c, how c is added. Your function is given, and you are adding c as a constant to the function. Now, if you look at the horizontal shift, look at this carefully. You are adding c not with the whole function, just with the x. Now, when you come up to, into this point, look at this. The 1 is added to the x. So that is the horizontal shift. Okay? And 2 is added to the whole function. That is your vertical shift. I'm saying, how do you know that which one is the vertical? Your question is a good question, but you know. So we'll also look at the reflection of the graph. That what kind of function can be written that will reflect the graph. For an example, if your original function is f of x, which is the black one, if you just change the sign of the graph and make it negative f of x, what does it mean? You are basically changing the sign of every single sign, right? Because if it is negative f of x, that means all the signs are changed. So you will still have the same graph, but that will be reflected like this. This is reflected, right? Do you feel that is reflected? That's reflection, some kind of reflection. Let's say, for an example, here you have like water. You see, the graph will be reflected. So that's why people feel like that's a reflection. Or something transparent, and the graph will be reflected like that. So anytime if you have a graph and you just change the sign of everything, for an example, let's say you have a graph. So you will be able to feel how the graph will look like. For an example, let's say somebody said that you have a graph like this: negative x plus 3 whole square. Now, first of all, you know this is a quadratic function, and you know that what is the standard quadratic function. You know that, right? Now, first of all, let's try to draw the standard quadratic function, which is, this is x square, right? I'm saying, okay, this is x square. Now, x plus 3, that means there is a horizontal shift, right? And it will go to the left. Now, let's say 1, 2, 3. So this is going to be your new graph. Okay. Now, since there is a negative sign, it will be reflected, right? So ultimately, let's see. So this graph is going to be reflected, so it will be look like this, right? So from this equation or function, you will know that this is going to be your graph, the red line. So you started from the standard quadratic function, right? And then you found that there is a plus 3, so you moved the graph, you shifted the graph horizontally. 3 units, right? By 3 units, because you see there is a plus 3, and you know for plus you just go to your left, and then you reflect it because there is a negative sign, and the negative sign means originally the graph was, what was the original graph? It was x square, right? There was no negative sign, right? Since there is a negative sign, that means even sometimes people do some kind of math like this. For an example, instead of having this, you might have, I'm just giving you some clue that how you can modify this. Instead of having this, you might have something like this, x square, let's see, minus 6x minus 9. But you know what? This is the same thing. Because if you just write the equation of a plus b whole square, this is what you will get. But what happens is when you look at this, you don't know exactly what it is, right? But if you can write it like this, in fact, doesn't matter how the graph is, the function is written. In most cases, you'll be able to write the function in some format like that. Something square minus something, okay? Even for an example, even you have, for an example, you have, let's say 10 here. For an example, you have 10 here. So you cannot feed the whole thing into a plus b whole square, right? So what you can do is, for an example, you can do this. Let me show you how you can just first put it into a pattern. So what you can do is you can just write like this, x square minus plus 6x. You know, you need 9, right? To put it into the formula, a plus b whole square, because it has to be 9, because it will be 3 square, which will be 9. So I put it like that, and I just keep one separate, because I had 10 in total. Now, you can write, this is a square, right, minus 2ab, oh, not minus, the plus b square, right? That was the formula, minus 1. So now you can write negative x plus 3 whole square negative 1. Now you can put another bracket here, make it positive 1. Now what do you have? You know that original graph is a standard quadratic equation, right? And that will be shifted to the left because of the horizontal shift here, right? And then it will be again shifted upward because of the vertical shift by 1, right? Once you have it, it will be reflected. So you know exactly what you need to do. You know what I'm saying? So it doesn't matter how the graph is written, you can always come up with something like this. You can do some algebra, and you can match with the pattern, and you can guess that how the graph will look like. You know, as you know, this is not, I'm not sure whether you will have, we don't have any such example in the book, but I'm just showing you that doesn't matter how the graph is, how the function is given, you can always tweak and twist and come up with something like this. And once you have it, you know that that is coming from the standard quadratic equation. So this is the standard quadratic equation with a vertical shift of, the horizontal shift of 3 to the left, vertical shift of 1 upward, and then reflection. After you have it, you just reflect the graph. So you can always guess that how the graph will look like. Even if you are discussing something, you can just visualize that how the graph will look like, even you don't want to exactly draw it. All right, so again, this is another example of reflection, but that's a reflection. You see here, there is a negative sign, and let's say this is the equation for the cubic root. Since there is a negative sign, we reflect it, but this is an example how that graph is being reflected. Do you see the reflection? Original graph is the blue one, and the red one is the reflected graph. And it's reflected because there is a negative sign. This is another example of the reflection for the square root. Now, how to obtain such, these are some examples that how can you reflect this graph. Do you remember how the x cube looked like? What is the graph of x cube? Yeah, something like S, but yeah, that was probably like this, right? For an example, let's say it was something like this, maybe x cube. That's the x cube. Now, how it can be reflected when it is negative x cube? Let me draw it. What do you think? The green one is the reflection of x cube, right? So you can think it partially. Maybe you will feel it better. Okay, let's say you think this side separately. You will see that this is a line which is being reflected here. Okay, and this line is reflected here. Okay, then you might feel it better. Just skip this part and think about only this side. So this line is reflected here, right? And this line is reflected here. That's how you can probably, I'm not sure, probably I would do that. How about this? Again, reflection, right? What is the original graph? How does it look like? Square root. How does the square root look like? Something like this, right? Square root. Let me erase the remaining part. How it will be reflected? -1, right? All right. So now we know about the vertical shift and we know about the horizontal shift. We want to know a little bit more. So there is a way you can stretch the graph or you can shrink the graph. It's also very simple. All you need to do is, for an example, you look at the blue line here in the left graph. That is your original graph, for an example. Let's say some function. Some function is there, okay? Now, if you multiply that function by a constant number, let's say by 3 or by 5, you're just multiplying the whole function. It is being stretched. Look at the red one. That is the same graph, but it's stretched, right? It looks like somebody is stretching the graph. And that C has to be larger than 1.
Show here the reflection with about the y-axis. You're going to do this way.
Let's see. I'm looking at backward. Okay. So okay. What was the question? Was it y-axis or x-axis? Yeah, if it is axis about y, yeah. Okay, so let's see. Let me go back to that. Okay, now I think we probably missed some point here. In these cases, square root, our reflection is about the y-axis. Okay, so whatever you have here, for an example, look at this one. This is a blue one, original one, which is reflected on the other side of y. Excuse me. When it is reflected about y-axis, whatever you have in one side of y, that will be reflected in the other side of y. Okay? But in some cases, we are reflecting about x-axis. So you will also be careful about which axis we are talking about. If it is about x-axis, now this is your x-axis, right? Now this will be reflected here. Oh no, for an example, this is the original graph. So this is reflected here, and this is reflected here, because this is about x, right? But in some cases, this is about y. So I think this is about y. So this should not be the right one. This is about y. So whatever you have in one side of y, because this is your y axis, right? So the other one will go here, because that is about y. If it is about x, it will be both sides of x. Now let's go back to our stretching one. Whenever you have a constant c multiplied with the function, your graph is stretched as long as the c is larger than 1. Okay, but if the c is smaller than 1, meaning if the c is between 0 to 1, which is a fraction, less than 1 but greater than 0, then it is shrink. The graph is shrink. Look at the second example. Here, the c is smaller than 1 but larger than 0. The original graph is the blue one. The shrink graph is the red one. So all these are different kind of transformation of graph. So look at the graph here. The original graph here, this is the original graph, the blue one, right? And look at the next graph. You are multiplying the graph by half. So you are multiplying by a constant number which is smaller than 1. So the graph should shrink. Do you think the graph is shrinked here? Remember, the shrinking is done vertically. Okay, so it should look like that you are basically pushing the graph like this. So at first look, it doesn't look like this is shrink, because if you look at this one, you will realize that over the time the graph will be expanding. But what happens is when you are shrinking this way, that expansion is done earlier, because you are pushing the graph this way, not this way. You are not shrinking this way. It's basically you are pushing vertically. Okay, so that's why that expansion, because the graph is being expanded. For an example, let me see whether I can draw it here, because it's not fully visible here. For an example, let's say your graph is, your graph is this. Now, look at this. Over the time, this is expanded, right? You see? Now, what happens if you push the graph like this? That expansion will come earlier, right? You see that expansion here, because you shrink the graph and you are pushing. That's exactly what happened in the red one, because you are pushing basically vertically. You'll be always, the graph is stretched and shrinked vertically, not the horizontally. So again, another such example. Here the graph is stretched. Now what happens? When the graph is stretched, it will be more narrower, because you are stretching vertically. Look at the difference. When in here, in 1, it was crossing this point, right? But here it was not crossing this point. It shrinked because you are basically stretching it. You have to feel it, because what happens? So if you are just stretching the graph, so all the expansion is deferred. You will see the expansion later. Whatever the expansion you see, this amount of expansion is coming here, because it's basically stretched. So what is this graph? Absolute function, right? It's a V, something like V, right? Now you are stretching the graph. What happens? Remember, you are stretching vertically. You are stretching the graph vertically. So it will basically shrink. What happens is this. You are stretching. So the original graph, let's say, look like this. Okay. Now let's say you are trying to pull those two lines. What happens? The line might look like this. It's interesting. It doesn't look like you are basically stretching. It looks like you are shrinking. You are basically stretching, because when you pull it, what happens? At this point, the expansion is this, but this kind of expansion will come later, because you are stretching. You are making 1 unit 2. Okay. You are basically zooming the graph, for an example. Okay, zooming in. All right, so we are combining here the both thing, horizontal stretching. So far whatever we did was the vertical part. So the vertical stretching and then vertical shrinking. Now how it becomes the horizontal shrinking and horizontal stretching? Again the same thing. Instead of multiplying the whole function by c, we are multiplying only the x by c. You see the difference? We are just multiplying the x, not the whole function. Now again, if c is larger than 1, it will be stretching. If c is smaller than 1 but the greater than 0, it will be shrinking. In the first example, here the blue line is the original line, and then your oh wait a second, what we are doing? Horizontally shrunk. Oh, I'm sorry. In this case, you are vertically shrinking. Yeah. So it's a little bit different, because if it is larger than 1, you are shrinking, and if it is 0 to 1, you are stretching. So the first example is about the shrinking. So when you have c larger than 1, you see the blue graph is the original graph and the red graph is the shrink graph. And here you see is between 0 to 1, and at this point, in this case, you are stretching the graph. So the blue one is the original graph and the red one is the stretched graph. This is an example how the horizontal shrinking is taking place. I think horizontal shrinking is a little bit easier to visualize than the vertical one. The blue graph is the original graph, and here you are multiplying the x by 2. You see the multiplication of x by 2. Therefore, that multiplication, you are basically shrinking the graph. And look at also carefully how you are shrinking. Look at this point. This was at 4. Now this point here is at 2. Why is that? Because you are shrinking by 2. Look at this. So it's something like, since you are shrinking by 2, what does it mean? It means that you are making it half. Do you understand what I'm saying? When you are saying I'm shrinking by 2, that means you are making it half. So exactly what is happening here. When you see this point came here, and even this point, it was 4 here. Now it is 2. But there is no change vertically, because you are doing everything horizontally. You see the vertical point is still at the same place. Negative 2, 4 is still negative 2, 4. Oh, I'm sorry, the negative 1, 4. Because the vertical, the horizontal one was shift, but the vertical point, which is up to 4, is still like that. So there is no change vertically, but there is a. But let's say, for an example, if you see the function is 4, what does it mean? 4x. It means that you are shrinking the function by 4. That means exactly what? You are dividing everything by 4 along the vertical line. For an example, in that case, this point would have been here, right? In 1. And this point would have been here. This is an example of stretching. Look at the example. We are multiplying by half. That means we are stretching it by 2 times. Same is true here. Look at this. This was in negative 4. Right now this is in negative 8. Because we are stretching by 2 times. This was in 4. This is in 8. If it is 1 over 3, that means what? You are stretching 3 times. If it is 1 over 5, you are stretching 5 times. But look at this. There is no change vertically, because the height of the graph was 4. Still the height is 4. Because vertically there is no change. Here the height was negative 2. That is still same. because we're not doing anything in vertical direction. Now, what is the graph? First of all, V graph, right? Absolute function. What you are doing? Stretching or shrinking? Everyone sure is shrinking? Because it's stretching. Look at the example. When you multiply something by, because in the case of the horizontal part, okay, you are stretching. So you are stretching the graph. Now what you are basically doing? For an example, when you stretch, how can you stretch the graph? For example, the graph is for an example V, and you are stretching. Let's say this is the original graph. Okay, you are stretching. It will be more wider. Maybe let's guess. It's 1/3, right? So for an example, let's say this point. Just as a guess, let's say this point is 1, 1. Remember, the height will be still 1, 1, but this will be, instead of 1, it will be, this point will be moved to 3, 1. So that line will be like this. Similarly here, because stretching means you are basically stretching horizontally. Okay, so every single x is multiplied by 3, but the y's are still same. So that's why 1, 1 is converted to 3, 1, because we changed the x. We just multiplied the x. It was 1, and we multiplied it by 3. It becomes 3. But x is still, y is still same. So this is the most important part. We learned several transformations. Now what happens when all the transformations come into the picture at the same time? Let's say you have horizontal shifting, vertical stretching, shifting, all this comes into the same time. This is the order you should follow. You will first do the horizontal shifting. Second, you will do the stretching or shrinking if you have any. Third, you will do the reflection. And fourth, you will do the vertical shifting. These are the order we follow when we have everything together at the same time. What do you mean by lot of line? At the end, you'll have just one graph, but you will be transforming the graph. So here is the summary, but we want to show you an example. For an example, here, look at this. Let's say this is the original graph, which is x square, and then you transform to move the graph to the left by 3 units, which is the horizontal shifting, right? That is what we do at the first. Then we do the stretching. So you stretch the graph by 2. Look at this. We multiplied the whole function by 2. You are stretching, right? What kind of stretching is that? Remember, we had 2 stretching, right? 2 different kind of stretching and shifting. One was vertical, the next one was horizontal. What kind of stretching we did? Let me show you again. This was the graph, and this is the new graph. It's the vertical one, right? And remember, in case of the vertical one, we multiply vertical stretching. The c is larger than 1, which is used to multiply the whole function. Here, the c is 2. So we multiplied the whole function by 2. Okay. Now, what is next? We do the, let's say, what we did here? Vertical shifting, right? We did the vertical shifting. Look at this. We just subtracted -1. That means vertical shifting. Since it is negative, you move downwards. So here are some examples, and let's try what we can do. Let's start with this one. Let's see how many examples. So we have a couple of examples. Let's start with this. Let's try this. Here you have a graph. So what you are doing, you have, what is the graph? It's f of x, which is, let's say this is your f of x, which is given. Okay? What you are doing here, look at this. What you are doing. First decide what you need to do. Your x is replaced by x minus 1. What does it mean? There is a horizontal shift, right? First of all, there is a horizontal shift. And the whole graph is multiplied by half. That means there is a vertical shrink. Shrink by what? Shrink by 2. Yeah, sure. Yeah. So the horizontal shift, we've moved the graph to your, which side? To your right, because it's negative 1, right? So you will move the whole graph to your right. This point will be here, right? And then this point will be here. Because you're moving 1 point, you're moving the whole graph, you're shifting the whole graph to your right. 1 point right. This point will be here. Now after that, you are multiplying the graph by half. What happens if you are multiplying the graph by half? You'll be shrinking the graph vertically, right? So when you shrink the graph vertically, remember the horizontal positions are still same, but all the vertical positions will be changed. This point was here, right? After the vertical shift. Then when you shrink, look at this. Since it is multiplied by half, you are shrinking by 2. That means this point will be here. It is at 3, right? It will be at 1.5. It's just by divided by 2, something like that. Because you are vertically you are shrinking. So at the end, your graph should look like, let me check whether I can draw it. Let's see. At the end, your graph should look like, let's see, x-axis, y-axis, and minus 1, minus 2. Let's say this is 1, 2, 3. At the end, the graph should look like this. It's 1.5. This is 2. We move to the right, right? And then 1, 2, 3, 4. This is coming to 2, going all the way to 4. This should be a graph because this is negative 2 because of the right shift. Right? The original graph was starting from negative 3. Because of the right shift, we are starting from negative 2. And then in the right side, instead of 1, we have 2 because we just moved the graph. And you see the graph stopped at 3, but here the graph will stop at 4 because of the right shift. And then for the shrinking vertically, at the top it was 3. Because you shrink by 2, so the 3 becomes 1.5. So that's what we did. This is 1.5 now. The green line is going to be the new graph. Any question about that? Let's see whether we can draw another one. It's the same graph, very similar graph, but look at the change and see whether you can draw it. First of all, you have to identify what happened. What things have happened? There is a vertical shift, right? There is a horizontal shift, and there is a reflection. If you want, please try and see whether you can draw the graph. Remember the sequence. The first one was the vertical shifting. The horizontal shifting. And the vertical shifting should be done at the end. In the middle, you will do the reflection. All right. Any answer? I think you cannot tell the answer for sure, but let's see whether we can draw it. Now, the first step is the horizontal shifting. Since it is positive 2, x plus 2, right? So the graph will move to the left by 2 units, right? So let's see whether we can draw the graph here. All right, see. That's 3, 4, 5. So 1, -2, -3, -4. So it's moving towards to your left. So here, so it will start from here all the way to 3. Let's see, it's 1, 2, 3. That point will be -2, -3 here. Okay, after doing the the horizontal shift, right? That's the first shift because of that x plus 2. We did the horizontal shift to the left by 2 units. Look at all the points are moved 2 units to the left. Even this point. It was at -1, 3. Now it is -3, 3, right? This is -3, 3 because this is 1, 2, 3. Now, what is the next step? Remember the sequence. We have a reflection here, right? We do the reflection before the vertical shift because the vertical shift has the least preference. We do that at the end. So the reflection about the x-axis, right? Now the graph will look like it's reflected, right, about the x-axis. You see the graph is reflected. It will be similar. I think this will be 1, 2, This is going to be 3. It's -1, -2, -3 now. And then this line will be same because it doesn't matter whether you reflect it or not, it will be still same. So let me erase this part. The graph is reflected. Now we'll be doing the vertical shift of -1. What happens if you shift that -1? You move upward or downward? You move downward, right? So all the points will be moved downward. So let's do a small trick because we are drawing in board, so we have the luxury of erasing. What we can do is instead of moving the whole graph, I will just move the y-axis here. Okay, that's the same thing because your graph will be still in the same place, so it will be here. This looks like that you are basically move the graph downward, but just pulling the y upward, but that's the same thing. So remember the points are changed. So this is right now -1, this is -2, this is -3, and this is -4. I think we need some practice. This chapter is extremely easy, but just looking at the equation and function, we have to do some practice to understand how we do this. Let's pick one example. So here, okay, couple of basic question. Use the graph of f of x equals to square root of x to graph of the negative x. The graph of g of x will appear in which quadrant? Remember, some of the reflection, this is a reflection, right? You see the negative x here? Some of the reflection is about x-axis, some of the reflection is about y-axis. This reflection was about y-axis. Okay, so that means what? This part of the graph will be reflected on the other side of y. So it will be in which quadrant then? Second quadrant, right? Because at this point the graph is at quadrant 1. So it will be at the second quadrant because this is quadrant 1, this is 2, this is 3, and this is 4, right? Any question? Next question here. Write the equation of the given graph g of x where the original function was x square. You know the x square. How the x square look like? X square should be standard quadratic form passing through the origin, right? But look at this, that how that point is moved here. So it was moved horizontally and vertically. Now how many horizontal positions was moved? Look at horizontal. Let's look at the horizontal shift first. How many horizontal positions was moved? Now 1, 2, 3, 4, right? So it will be x minus what? 4, right? Because it moves to the right. When you are moving right, it's negative, right? Horizontally, if you move right, it becomes negative. Now, so by that, you know that your answer will be either of these two. You can rule A and C because horizontally right, which is negative, it must be x minus 4. Now, what is the vertical move? Downward, right? Which is negative. So the right answer is A then. Oh, right answer is B because we ruled out A and C. So x minus 4 whole square minus 3. This is minus 4 because you are moving to the right 4 unit and you are going downward because of the vertical shift. So you will see a lot of such question. Okay, here this is a V graph. What happened here? You have a reflection, you have a horizontal shift. Now for the horizontal shift, how many positions you moved? 1, 2, 3, 4 positions, right? To the right, it will be x minus 4. So this is x minus 4 and there is a negative. Negative should be should precede the whole function. Okay? Because one of the problem with the absolute function is if you put the negative inside, that might be cancelled out because of the absolute sign. You cannot put that. So it will be, it's probably pretty simple, which is A. Okay? So now you should try section 1.6 homework. But before that, make sure you finish all the homework up to 1.5. And 1.5 will remain open until tomorrow night, midnight. And 1.4 will remain open until tonight, midnight. Okay? Say it again. Yeah. For 1.4 and 1.5 we just finished today, so that's why I extended. Because you have unlimited chances. If you already got 100%, don't try it. But I think for section 1.5, since we could not finish it by Friday, it's not fair, so I extended the deadline up to tomorrow. But 1.6 and starting from 1.6 to like 4.2, those will be due until will not be due until next Sunday.